Okay, students, so let's start with today's past papers. Today we are going to do AS Physics MCQs for the topic of elastic deformation. A spring has a spring constant of 6 newtons per centimeter. It is joined to another spring whose spring constant is 4 newton per centimeter. Okay. A load of 80 newton is suspended from the composite spring. Perfect. What is the extension of the composite spring? We have to calculate the total extension. Okay. So can you see the two springs are in series? So this will also receive 80 Newton. This will also receive 80 Newton. Apply force is equals to Ke. Force is 80, K is 6. Your extension here or the extension of the first spring comes out to be what? The extension of the first spring comes out to be 80 divided by 6. This comes out to be 13.3 centimeter. Let's do that for the second spring as well. F is equals to Ke. The force is 80. The spring constant is 4. Extension is E. Extension comes out to be 20 centimeter. Perfect. So for the first spring, you have an extension of 13.3 centimeters. For the second spring, you have an extension of 20 centimeters. If you combine them together, the total extension becomes 33 centimeters. D is your answer. And if you check the marking scheme that is attached in the description below as well, the answer will be D. Let's move on to here. Which arrangement has the largest combined spring constant? Okay. Here I have to discuss one thing with you guys. The spring constant is always inversely proportional to extension. Spring constant is always inversely proportional to extension. Okay. So, which of these combinations will give the smallest extensions? Which of these combinations will give the smallest extensions in which all the springs are connected in parallel? Always remember one more key point here to remember. Least extension occurs when all springs are in parallel. All springs in parallel. Are there any options like that? Yes. B. If you have least expansion here or least extension here, your spring constant will be the largest. B is your answer. Simple as that. Let's further move ahead. A copper wire has a diameter of 1.6 millimeter. It is stretched within its limit of proportionality by a tensile force of 430 newtons. Perfect. The Young's modulus is this. We have to calculate the strain in the wire. Okay. We have studied that Young's modulus is what? Stress over strain. Okay. What is the Young's modulus? 130 gigapascal, 130 into 10 raised to the power of 9. What is the stress? Force. Your force is 430. Your force is 430. Okay, so in place of stress, we will write 430 divided by what will be the area? You are given the diameter. Can you calculate the area? Yes. Pi over 4 into diameter 1.6 into 10 raised to the power of minus 3 whole square divided by the thing that you have to calculate, that is the strain. This is what you have to calculate. Perfect. So 430 divided by pi into 1.6 into 10 raised to the power of minus 3 whole square. Perfect. And you can also consecutively calculate the, one second, you can calculate the strain here as well. Yep. Divide it by 130. Divide the answer by 130 into 10 raised to the power of 9. The strain comes out to be 1.64 into 10 raised to the power of minus 3. C is your answer. And if you check in the marking scheme, the answer to question number 3 is C. Perfect. Let's further move ahead. Now, let's see this. An elastic cord of unstretched total length 16 centimeter, cross sectional area this. So you are given the length L, you are given the cross sectional area A, is held horizontally by two smooth pins 8 centimeter apart. Perfect. The cords obey Hooke's law. a load of mass 0.4 kg is suspended centrally on the cord. The angle between the two sides of the cord is 60 degree. Okay, perfect. What is the Young's modulus? Now, first of all, let's write down the formula for Young's modulus. Young's modulus is FL over AE. Perfect. You are given the length here. Yes, that is 16 centimeter. You are given the area here. Yes, that is 2 into 10 raised to the power of minus 4. You have to somehow deduce force and extension. Extension is pretty easy to deduce. Initial length was 16. What is your total length now? 8, 8. And this will also be what? 8. Why? Because this is an equilateral triangle. If you are good at maths, analyze 60 degree corresponds to 8 centimeters. This 8 centimeter will have a corresponding angle of 60 degree. 60, 60. What is the remaining angle? 60 degree here. This side will give 8 centimeter as your answer. So extension is also known to you, that is 8 centimeter. How? Because the original length was 16 and now the length is 8 plus 8 plus 8, that is 24. Okay. Now the only thing that is left is to calculate the tension in the cords. You only have to calculate the tension in the cords. How will we do that? What we can do is we can divide this diagonal tension force like this. Like this. Okay. What will be the value of this blue force? T cosine 60. And there are two such forces, so it will be 2t cosine 30. Perfect. And what is the force opposing these two forces? The weight of the mass 0.4 into 9.81. Okay. So what can we do? We can say that 2t cos 30 is equals to 0.4 into 9.81. Can you calculate tension? Yes. 0.4 into 9.81 divided by 2 cos 30. The answer comes out to be tension is 2.6. Tension is 2.26 newtons. Perfect. Now you have the force as well. Can you now calculate the Young's modulus? Yes, now it's easy to calculate the Young's modulus. Young's modulus is equals to 2.26 into the length, that is 16 centimeters, 16 into 10 raised to the power of minus 2, divided by the area, that is 2 into 10 raised to the power of minus 4, multiplied by the extension, that is 8 centimeter, 8 into 10 raised to the power of minus 2. Let's see what our Young's modulus comes out to be. 2.26 into 10 raised to the power of minus 2 into 16 divided by 2 into 10 raised to the power of minus 4 into 8 into 10 raised to the power of minus 2, I guess. Yes. Minus 2. What is your answer? Your answer comes out to be. Am I missing something? Yeah, one thing. This is 10 raised to the power of 6. Yeah, that's why the answer is coming out to be incorrect. Let's substitute the values again. The answer comes out to be 2.26 into 10 raised to the power of 6. 2.26 into 10 raised to the power of 6. C is your answer. Let me check in the marking scheme. Yes, C is your answer. Let's further move ahead. A known tensile force acts on a metal wire. The wire does not exceed its limit of proportionality. Which two measurements enable the strain of the wire to be calculated? The unstretched length of the wire and the cross-sectional area? No. The unstretched length of the wire and the extension? B is your answer. If you check in the marking scheme, the answer to 7 is B. Perfect. Let's further move ahead. Okay, let's see this. A wire is extended by different forces. The wire obeys Hooke's law. Perfect. A graph is plotted to show the variation of a quantity y with quantity x. Okay. So if the wire is obeying Hooke's law, this can never be a force versus extension graph. Because if the wire was obeying Hooke's law, the force versus extension graph would have been linear. So B and C options get cancelled out. Now A and B have the same option. So let's write down the formula of elastic potential energy 1 upon 2 kx square. Perfect. And this looks like a graph of what? This looks like a graph of y is equals to under root 2. Okay. Let's say I make extension the subject here. Let's say I make extension the subject here. Let me, yeah, change the color of the highlighter. 2 into elastic potential energy divided by K is equals to your extension square. This entire thing is a constant. Perfect. X square is directly proportional to elastic potential energy taken under root on both sides. X is directly proportional to elastic potential energy. So we can plot X, that is extension on the y axis, and elastic potential energy on the x axis. Any answers like that? Yes, A is your answer. Because this graph, this shape of the graph is always the graph of y is equals to x under root. So we had to make an equation that satisfies this. D cannot be your answer. Why? Because if you plot elastic potential energy on the y axis, then it would have been a quadratic curve. It would have been a quadratic curve. It wouldn't have suited the curve that is given in the question. Okay, let's see. Identical springs are joined in 4 arrangements. Which arrangement has the same spring constant as a single spring? Perfect. So, which spring will have the same spring constant as a single spring? Let's see that. If you see here, the extension is E, the total will become 2E, the spring constant will become half X. Because the spring constant and extension are inversely proportional. If you see here in parallel, this will be 1 upon 2e, 1 upon 2e. The spring constant will become 2k. If you see here 1 upon 2e, 1 upon 2e, they will get added up. Total extension will be e. Spring constant will be k. C is your answer. Perfect. Let's further move ahead. Okay, let's see. These two wires P and Q are made from same metal. Okay. What does this signify? Same metal. This means they will have the same Young's modulus. Okay, and hang vertically from a steel girder. Okay, wire Q has half the length and twice the diameter of P. Perfect. Identical masses are attached to the bottom of each wire. Both wires obey Hooke's law as they are stretched by weights of the masses. What is the ratio of extension of wire P divided by the extension of wire Q? So the best method is to make partitions and write everything. The Young's modulus of P is E. The Young's modulus of Q is E. Perfect. Wire Q has half the length. So wire Q will, let's say, have half L. This will have L. And twice the diameter. Okay, so let's say this has twice the diameter. This has D. Perfect. Now, what do we have to calculate? We have to, okay, identical masses are attached. That means forces will also be similar on both of them. Perfect. You have to calculate the ratio of extension of P divided by extension of Q. Perfect. First of all, do you remember this formula? First of all, do you remember this formula? Young's modulus is equals to FL over AE. Can I make extension the subject here? Yes. Extension is equals to what? Extension is equals to FL over A, capital E. Perfect. Let's calculate the extension of P. Let's calculate the extension of P. What is the force? F. What is the length? L. What is the area? A. What is the Young's modulus? E divided by the extension of Q. Perfect. F into the length is half L. Perfect. Into the area. What will happen to the area? If the diameter has doubled, always remember if the diameter doubles, let's say the diameter is going from D to 2D, what will happen to your area? Your area will go from A to 4A. Your area will go from A to 4A. So wire Q will have an area of 4A. Young's modulus is same, that is E. Anything's getting cancelled out? Yes, there are many things that will cancel out. FL, FL, AE, AE, perfect. And this gets divided here. Sorry, A will get cancelled out, not 4. 1 second. A will get cancelled out, not 4. Perfect. 1 upon 2 divided by 4, it becomes 1 upon 8. 8 goes to the top side. The ratio becomes 8 over 1. A is your answer. Let me see. The answer to 11 is A. Perfect. We are going good today. Let's see this. 3 springs are arranged vertically as shown. Perfect. Spring P and Q are identical and each have a spring constant K. Okay, this has a spring constant K. This has a spring constant K. Perfect. A spring R has a spring constant 3K. Perfect. What is the increase in overall length of the arrangement when a force of W is applied? Perfect. So if a force of W is applied, this series spring will receive the entire force. However, the springs in parallel will receive what? W upon 2 and W upon 2. Simple. Can we calculate the extension here? Yes. Extension is equal to what? W over 3K. Perfect. Can we calculate the extension of this? Yes. W over 2 over K. Perfect. Can we add up these two extensions? Yes. E1 plus E2. Can we add up these two extensions? W upon 2K plus W upon 3K. Let's take an LCM. Multiplied by 3, multiplied by 3, multiplied by 2, multiplied by 2. 3W plus 2W over 6K. It comes out to be what? 5W over 6K. Your answer comes out to be A is your answer. So if we check, the answer for 13 is A, correct. Let's further move ahead. Okay, let's see this. A steel bar of circular cross sectional is under tension T as shown. The diameter D of the wider portion is double the diameter of the narrow portion. Okay. So if this is 2D, this will be D. Perfect. What is the value of the stress in the wider portion divided the stress in the narrow portion? Perfect. So what have we studied? Stress is equals to force over area. Perfect. In the wider portion, what is the force? In the wider portion, let me do it like this. Stress for the wider portion, force of F, or you can say the force of T divided by what is the area? Area will be 4A since the diameter is double. For the narrow portion, the force is still T and the area is A. Divide both of them. T over 4A divided by T over A and A cancel out, T and T cancel out, 1 over 4 or 0.25 is your answer. A is your answer. 15's answer should be A. Perfect. Let's further move ahead. Let's see this. The spring constant of 4 springs are determined by plotting the following graphs of force against extension. Okay. Which order of the graph shows decreasing spring constant? Okay. Which order of the graph shows decreasing spring constant? Okay. Let's calculate the spring constant of 1. That is 10 force divided by 5 millimeter. This comes out to be what? 2 Newton per millimeter. Let's calculate this as well. 20 divided by 4 will give you what? 5 Newton per millimeter. Let's calculate for this as well. 100 divided by 0.1. This comes out to be what? 1000 Newton per millimeter. Let's calculate for this as well. 10 divided by 0.5. This gives you 20 Newton per millimeter. Okay. Shows decreasing spring constant. So you must start with the largest spring constant. Which has the largest spring constant? 3. Perfect. So there is only one option starting with 3. B is your answer. Perfect. The answer to 17 is B in the marking scheme as well. Let's further move ahead. Okay, let's see this interesting question. This is a very interesting question. A student is investigating the mechanical properties of a metal. Perfect. He applies different loads to a thin wire up to its breaking point and measures the extension of the wire for each load. He then plots a graph of stress against strain. Perfect. This is the stress versus strain graph. Perfect. The student repeats the experiment with a wire made from the same metal. If your wire is made from the same metal, what will happen? Your Young's modulus or E remains same. If your E remains same, then your stress strain graph will be same as well. Perfect. So what will be the stress strain graph here? You should have 4 on the y-axis and 40 on the x-axis. Any graphs that resemble this? B is your answer. And if you see this question number 19 and check in the marking scheme, the answer of 19 is B. This looks like a complicated question, but if you realize that same metals will have the same Young modulus and same stress strain graph, then you don't need to study the entire question. Okay, let's see this question. The diagram shows a simplified model of a building with four identical heavy floors. Perfect. The spacing of the bottom floor from the ground is twice that of the spacing between the floors. Between each floors are equal number of vertical steel supporting rods of negligible mass compared with the floors. Perfect. The rod of different diameters so that stress in each rod remains same. Perfect. These top rods and bottom rods are of different diameters, so the stress in each rod remains same. What is the ratio of the diameter of bottom rods divided by the diameter of top rods? How can we calculate the ratio of the diameter of bottom rods divided by the ratio of the diameter of top rods? First of all, if you analyze what will be the force acting on the top rods, W weight. If the stress of the top rod is W over 80, we can say that weight over the area of the top rods. What will be the stress of the bottom rods? This also has a weight, this also has a weight, this also has a weight. So collectively, bottom rods will be facing a force of what? 4W divided by the area of the bottom rod is equals to stress. Since both these stress are same, we can equate them. W over top rod area is equals to 4W over bottom rod area. W cancel out. And you have to calculate area of bottom rod divided by area of top rod is 4. But you have to give the ratios of diameter. Pretty easy. If you have reached till here, then the ratios of diameter is also easy. Do you realize that area is equals to what? Pi du square over 4. Area is directly proportional to what? Du square. So if we take a square root on both sides, we will get the diameter ratio. Diameter B over diameter T is equals to under root 4. That is equals to 2A is your answer. Let's further move ahead. Let's see this. The graph shows the effect of applying a force of up to 5 Newton to a spring. Perfect. The spring obeys Hooke's laws for forces up to 7 Newton. What is the total extension produced by the spring by a 7 Newton force? Perfect. So if you are applying a 5 Newton force, your spring length goes from 11 to 14. There is an extension of 3 centimeter. What will be the extension when you apply a 7 Newton force? Just apply a ratio method. If 5 Newton is causing an extension of 3 centimeters, 7 Newton will cause an extension of x cross multiplied. X comes out to be what? 7 into 3 divided by 5. Your extension is 7 into 3 divided by 5. This comes out to be 4.2. Do you have to give the total extension? Yes. So you don't have to add the original length. Perfect. Let's further move ahead. What is the Young's modulus of the material of the wire? You have to calculate the Young's modulus of the material of the wire. Now always remember that the Young's modulus can only be calculated in the linear region. Young's modulus can only be calculated in the linear region of stress versus strain. Let's calculate the gradient here. 2.1 into 10 raised to the power of 8 divided by strain, that is 1.4 into 10 raised to the power of minus 3. Can we calculate the Young's modulus here? Yes. 2.1 into 10 raised to the power of 8 divided by what? 1.4 into 10 raised to the power of minus 3. This gives you an answer of what? 1.5 into 10 raised to the power of 11. If you check the answer for 23, it is D. Perfect. Let's further move ahead. Let's see this. A wire of 0.8 meter length of steel and a 1.4 meter wire of brass are joined together. The combined wires are suspended from a fixed support and a force of 40 Newton is applied as shown. Okay. The Young's modulus of steel is this. The Young's modulus of brass is this. Each wire has a cross-sectional area of this. The wire extend without reaching their elastic limit. What is the total extension? Ignore the weights of the wire. Perfect. So you have to calculate the total extension. First of all, visualize that extension has a formula of what? Force into length divided by area into extension. Perfect. What is the force here? 40 Newton, 40 Newton. Perfect. First of all, let's calculate the extension of steel. What is the force on steel? 40. What is the length of the steel wire? 0.8. What is the area of the steel wire? 2.4 into 10 raised to the power of minus 6. Perfect. What is the Young's modulus of steel? 2 into 10 raised to the power of 11. Can you calculate the extension of steel? Yes. 40 into zero point 0.8 divided by 2.4 into 10 raised to the power of minus 6 into 2 into 10 raised to the power of 11. This gives you an answer of what? 6 point. The extension of steel is 6.67 into 10 raised to the power of minus 5. Perfect. Can you calculate the extension of brass? Yes. What is the force on brass? 40. What is the length of brass? 1.5. What is the area of brass? 2.4 into 10 raised to the power of minus 6 multiplied by the Young's modulus of brass, that is 1 into 10 raised to the power of 11. Let's calculate the extension here as well. 40 into 1.4 divided by 2.4, sorry. 2.4 into 10 raised to the power of minus 6 into what? 1 into 10 raised to the power of 11. What will your answer come out to be? 2.3 into 10 raised to the power of minus 4. Add this with 6.67 into 10 raised to the power of minus 5. What does your total extension comes out to be? 3 into 10 raised to the power of minus 4. If you check in the marking scheme, the answer is B. Perfect. We are going on the right track. Let's further move ahead. Okay, let's read this question out. In an experiment to measure the Young's modulus of a metal, a wire of diameter 0.5 millimeter is clamped as shown. Okay. The wire passes from a clamp around a frictionless pulley and then to a second frictionless pulley when loads F are applied to it. A marker is attached to the wire, so the total length between the clamp and the marker is 3.7 meters. So this is your L. A scale is fixed near to this marker. The graph shows how the reading on the scale varies with F. Perfect. What is the Young's modulus of the metal? So first of all, you have to realize that Young's modulus is equals to what? FL over AE. You can easily calculate F over E if you look at the graph. You can take 2 points on the graph. Let's say the force is 10 when the extension is 8 millimeter or when the marker is giving a reading of 8 millimeter, and the force is 4 Newton when the marker is giving a reading of 6 millimeter. So here the force is 4 Newton, here the force is 10 Newton. For an increment in force of 6 Newton, what is your increase in extension? 2 millimeter. Extension increases by 2 millimeter. Can you calculate K or force versus extension? Yes, force versus extension, or K is equals to what? 6 divided by extension, that is 2 into 10 raised to the power of minus 3. 6 divided by 2. This will go to the top side. This will become 3 into 10 raised to the power of 3 Newton per meter. Perfect. Let's substitute it here. 3 into 10 raised to the power of 3. Your length is 3.7. Perfect. What is your area? Area is pi over 4 into the diameter square, that is 0.25 millimeter. 0.25 into 10 raised to the power of minus 3 whole square. Okay. So let's see this answer. 3 into 10 raised to the power of 3 into 3.7 divided by pi over 4 into what? Into 0.25 into 10 raised to the power of minus 3 whole square. Your Young's modulus comes out to be 2.26 into 10 raised to the power of 11. The answer for 27 should be D, and in the marking scheme as well it is D. Let's further move ahead. Okay, let's see this. An elastic material with a Young's modulus E is subjected to a tensile stress S. Hooke's law is obeyed. What is the expression for the elastic energy stored per unit volume? So if you remember that the area under stress strain graph, the area under stress strain graph used to be equal to your elastic energy per unit volume. So this area is equals to what? 1 upon 2 into stress into the strain. Stress into strain. Now here you aren't given any symbol for strain. So you can replace a strain by Young's modulus. What do I mean by that? Young's modulus is equals to stress over strain. You can say that strain is equals to what? Stress over Young's modulus. Perfect. Let's replace it here. 1 upon 2s into s over e. This becomes what? S square over 2e. Your answer is A. Let me see this question number 28. The answer to 28 should be A, and it is A, perfectly correct. Let's further move ahead. Okay, let's see this. Two wires, one made of brass and the other made of steel, are stretched in an experiment. Both wires obey Hooke's law during the experiment. So directly A and C will get cancelled out, because if you are obeying Hooke's law, your stress versus strain graph will remain same. The Young's modulus for brass is less than the Young's modulus for steel. This means brass will have a lower gradient. Steel will have a higher gradient. B is your answer. Let me check this as well. The answer to 31 should be B, and it is B. Correct. Okay, let's try this question out. A wire is fixed at one end and extended by a force that is applied to the other end. The force is slowly increased from 0 and then slowly decreased back to 0. The force extension graph for the wire is shown. The graph line for the wire being loaded is the same as the graph for being unloaded. Perfect. Which statement about the deformation of the wire is correct? Can you see there are no permanent extensions here? That means the graph is only undergoing elastic deformation. B is your answer. If you check in the marking scheme, 59 has an answer of B. Perfect. Let's move ahead. Let's see this. A platform is suspended by four steel wires. Each wire is 5 meters long and has a diameter of this. The Young's modulus of steel is this. The wire obeys Hooke's law when a mass of 200 kg is placed on the platform. Okay. How will the platform descend because of the extension of the wire? Okay, how far will the platform descend due to the extension of the wire? Perfect, perfect, perfect. So, first of all, what is the examiner asking you exactly? The examiner is asking you for the extension. We know extension is equals to force into L divided by area into the Young's modulus. Perfect. Now, here you have to pay attention that the 200 kg mass is getting divided among four wires. So, the force will be equal to what? 200 kg into 9.81 divided by 4. This comes out to be what? Let's calculate this. 200 into 9.81 divided by 4. This gives you an answer of what? 490.5. 490.5 newtons is your force. Perfect. Let's place it here. 490.5. Your length is 5. Perfect. What is your area? You aren't given the area, but you are given the diameter. Pi over 4 into the diameter, that is 3 into 10 raised to the power of minus 3 whole square. What is the Young's modulus? 2.1 into 10 raised to the power of 11 pascals. Can we calculate the extension? Yes, surely we can do that. 490.5 into 5 into 5 divided by what? Pi upon 4 into 3 into 10 raised to the power of minus 3 whole square into 2.1 into 10 raised to the power of 11 comes out to be. What does your extension of the wire comes out to be? 1.65 into 10 raised to the power of minus 3 meters. Any options like that? C is your option. Let's check on the back marking scheme as well. 62. Answer is C. Perfect. We are going good. Let's move on to the next question. Okay, let's see this. A spring has an original length of 100 millimeter, is compressed by a force. Perfect. The graph shows the variation of length of the spring with the compressing force. Perfect. What is the energy stored in the spring when the length is 70 mm? Okay. When the length is 70 mm. Here. Perfect. When the length is 70 mm, what is the compression? The compression is 30 mm. You can say the compression or the extension is 30 mm. What is the force being applied? Force being applied is 6 Newton. Can you calculate the strain energy? Yes, 1 upon 2 Fe. What is the force? 6. What is the extension? 30 into 10 raised to the power of minus 3. This comes out to be what? 6 into 30 into 10 raised to the power of minus 3 divided by 2. This gives you an answer of what? 0.09 joules. A is your answer. The answer to 67 should be A, and it is A. Let's further move ahead. Okay, let's see this. Forces are applied to the ends of a rod so that its length increases. The variation with load L of the extension of a rod is shown. Perfect. Force versus extension graph is basically given, where P is the elastic limit. Perfect. Which shaded area represents the work done during the plastic deformation of the rod? Okay. We have to tell the work done during the plastic deformation of the rod. So after elastic limit, plastic deformation happens, and work done by the plastic region is the area with the extension axis. I guess C is my answer. Let me confirm it as well. The answer to 73 is C. Perfect. Perfect. The answer to 73 is C. Let's further move ahead. Let's see this. Okay, let's see this. A cable on a suspension bridge supports a weight of this. This weight causes the cable to stretch by 47 millimeter. Perfect. A lorry crossing the bridge then increases the force of the cable to this. The force versus extension graph for the cable is this. Perfect. What is the increase in strain energy of the cable when the lorry is crossing the bridge? We have to calculate this additional strain energy. This is basically what? This is basically a trapezium. How can you calculate the additional strain energy here? By calculating the area of this trapezium. 1 upon 2 into sum of parallel sides, that is 19.3 into 10 raised to the power of 5 plus 23.3 into 10 raised to the power of 5 multiplied by a height, that is 57 minus 47, that is 10 millimeter. 10 into 10 raised to the power of minus 3. Let's calculate the answer. 19.3 into 10 raised to the power of 5 plus 23.3 into 10 raised to the power of 5. Okay. Multiplied by 10 multiplied by 10 raised to the power of minus 3 divided by 2. The additional strain energy comes out to be 21 kilojoules. The answer to 76 should be A, and it is A. Perfect. Let's further move ahead. Okay, so let's see this question as well. The diagram shows a large crane on a construction site lifting a cube shaped load at constant speed. Perfect. A model is made of the crane, its load, and the cable supporting the load. The material used for each part of the model is same as that in the crane, cable and load. The model is 1/10 size in all linear dimensions. Okay. What is the ratio of stress in the cable on full size divided by the stress in the cable on the model crane? First of all, analyze that stress is equals to what? Force over area. Okay. What can the force in the cable be represented by? The force in the cable will be the weight in the block. Okay, so weight divided by area. Perfect. What will the weight of the block be equal to? Mass into gravitational field distance divided by the area of the cable. What is the area of the cable equal to? Pi over 4 d square. Perfect. Can I place something in place of mass? Can I place a linear dimension in place of mass? Yes. Density into volume into g. The 4 comes to the top side divided by pi du square. And can you realize that this load is a cube? What will be the volume of this cube? The volume of this cube will be equal to L cube G divided by pi d square. This is the formula for stress for this question. Perfect. Now, in the full size screen, let's write down the heading. In the full size screen, you will have length L, diameter D. Perfect. Your stress will be equal to what? 4 rho L cube D, L cube G over pi D square. Perfect. In the model, what will happen? You will have 110L and 110D. Perfect. Stress in the model will become what? stress in the model will become what? 4 density 1 over 10 L cube into G divided by pi 1 over 10 D square. Okay. What can you see? What can you see? This will become rho density G and 1 over 1000 L cube divided by pi into 1 over 100 d square. This will get cancelled out with this two zeros and only 1 over 10 will be left. So the stress in the model will become what? The stress in the model will become 4 density G and L cube divided by 10 pi, okay, and d square. I hope I have written it correctly. Now let's calculate the stress in model, the stress in full size divided by the stress in model. What is the stress in full size? 4 density L cube G divided by pi d square divided by 4 density G L cube. What will happen? This thing can get cancelled out with this thing divided by 10 pi d square. Pi d square gets cancelled out with pi d square. This 10 will come into the numerator. The answer comes out to be 10 ratio 1. This is your answer. C is your answer. I hope I am correct. Let me check in the marking scheme. The answer for 33 is C. Yes, I am correct. Perfect, perfect. So what have I actually done? First of all, I have calculated a formula for stress. Stress is equals to force over area. What is the force in the cable? The weight of the load. How to calculate the weight of the load? Mass into gravitational field strength. What is another formula for mass? Density into volume. What is the formula of area? Pi upon 4 d square. 4 comes to the top side. This is your formula for stress. Here, in place of volume, I have substituted L cube. Why? Because volume is equals to L cube because it is a cube. Now, in the full size model, the stress will be what? 4 into density into L cube into G divided by pi d square. In the model, what will be the stress? Force, that is 4 pi L, that will become 1 upon 10 L, since everything in the model has become 1 upon 10. Then you solve this and you get this as your stress in the model. This was your stress in the full size. You divide both of them, you get 10 over 1 as your answer. C is your answer. Perfect. A little messed up, but yeah. Let's further move ahead. You have to calculate the stress at y divided by the stress at x. Okay. It is subjected to a tensile force. Perfect. So what is the stress at y? The stress at y is equals to force, tensile force divided by the area. That will be what? Pi d square over 4. This is the stress at y. Perfect. What will be the stress at x? Stress at x is what? Tensile force F divided by pi. This time your diameter is 2d whole square divided by 4. This becomes what? 4F divided by pi, and this will become 4d square. So this will become 4 pi d square, and this, if we take it on the top side, 4F divided by pi d square. We have to calculate the ratio of stress at y divided by the ratio of stress at x. Can we do that? Yes. What is the stress at y? 4F divided by pi d square divided by 4F divided by 4 pi d square. Perfect. Is anything getting cancelled out? Yes. 4F gets cancelled out. Pi d square gets cancelled out. 4 over 1 is your answer. The answer to 34 is D, and in the marking scheme it is D as well. Let's further move ahead. Okay, let's see this. A wire of diameter D and length L hangs vertically from a fixed point. The wire is extended by a hanging mass M on its end. The Young modulus is E. The cross sectional area is G. Which equation is used to determine the extension? Extension E is equals to what? FL over AE. Can you like break up area? Yes. FL over area is pi du square over 4 into Young's modulus. 4 comes to the top side. 4FL divided by pi du square E. Okay. Can you further do something? Yes, I can break down this force into what? I can break down this force into what? Mass into gravitational field distance. mg L pi du square E. What is the answer here? D is your answer. The answer to 36 is D in the marking scheme as well. Perfect. Let's further move ahead. Which force versus extension graph shows plastic deformation of a sample of a material? Perfect. For plastic deformation, there is permanent extension. For plastic deformation, there is permanent extension in this spring. So in A, if you are loading like this, you are unloading in the reverse direction. There is no permanent extension. No permanent extension in B as well. Not in A, not in C. You can only see a permanent extension in D. That is this thing. This is your permanent extension in D. D is your answer. Perfect. Let's further move ahead. Okay, so let's read this question out. Compressive forces are applied normally to end faces of a cylinder of initial length L. Perfect. The cylinder is compressed by the forces so that its length decreases to 0.6 L. Initially, your length was L. You apply compressive forces, your length decreases to 0.6 L. After compressive forces are removed, the cylinder length increases to 0.8 L. Okay, there is a weird situation happening here. When you applied the force, your length decreases to 0.6 L. When you remove the force, it only increased to 0.8 L. This is a sign of plastic deformation. And along with plastic deformation, before plastic deformation, what happens? Elastic deformation. So both plastic and elastic deformation are happening here. A is your answer. Simple as that. Let me see 58. If I go here, yes, 58 has an answer of A. Now, most students will get how plastic deformation is happening because the end length is less than the original length that we started with. Can you see 0.8 L is less than L, the length which we started with? Hence, plastic deformation is happening. But most students will ask, sir, why is elastic deformation also happening? Always observe that in a force versus extension graph, you can only reach the plastic region once you have gone through the elastic region. So, elastic deformation will happen till the elastic limit, and then you will have plastic deformation. So, in any kind of plastic deformation, there will be always some kind of elastic deformation as well, because you cannot go towards plastic deformation unless and until you pass through the green portion, that is the elastic deformation portion. A is your answer. Let's see this. A sample of material is stretched by a tensile force to a point beyond its elastic limit. The tensile force is then reduced to zero. The graph of force against extension is shown below. Perfect. Which area represents the net work done on the sample? Okay, which area represents the net work done? What is the work done that is left after loading and unloading? If you notice, during loading, this entire region was your work done. However, during unloading, you only recovered this. So what is the net work done or the remaining work done? X plus Y. B is your answer. This marks the end of the past papers for elastic deformation. If you have any questions, you may ask in the chat.